let's talk a little bit about effect size. What is it and why is it important? There's a good review of this in your hardcover textbook. This is part of the assigned reading we've already had on page 349. The way they describe effect size is that it is the proportion of the variance accounted for by the treatment in question. Now, that sounds like a mouthful, but we'll talk about it in terms of the particular statistical analysis we did this semester. We did a factorial ANOVA design. There are many different measures of effect size depending on which stat you perform. For us, since we did a factorial ANOVA, one option for measuring effect size is called an eta squared score. First thing to mention, since you're going to be writing up result sections, you will not necessarily be reporting the eta squared or effect size numbers in your paper. You only report an eta squared score, and you only talk about effect size if you had a statistically significant effect. So if you're doing a factorial ANOVA design with two variables, it would be possible to have three separate effects. You could have two statistically significant main effects and a statistically significant interaction. So you could be reporting three separate effect sizes and talking about those separately in theory. However, it's also possible that you did not find any difference between your research groups, right? Maybe you didn't find a significant main effect or a significant interaction. In that case, if you didn't find any significant effects, you wouldn't report any effect sizes. Why? Because there wasn't an effect. So if you don't have an effect, you don't talk about an effect size. You only report for statistically significant effects. So if there's no statistically significant effects or difference between groups, that means there's no evidence that there was an effect of that variable, which means you don't report effect size. Okay, so what exactly is an eta squared score or an effect size score? Well, I do want to mention how you would describe this. We said that effect size is a measure of variability that's due to a particular variable that you're studying, right? So one way to word this in your paper, and I'll be talking to each group about this as we look at your analyses and see if you have a significant effect, is if you have one, a way to describe it is this way. You'll have an eta squared score or number, and you would use that number multiplied by 100 to say, this is the, 6, 20, 30, some number here goes here. 30% of the variability in the data can be accounted for. If it was an interaction, you would describe it as by the interaction between your two variables. If it's one of your main effects, it is that a certain percentage of the variability in the scores that you got for your data, this is whatever your DV is, they can be accounted for by that particular main effect. And we'll go over some specific examples to make sure this is clear in just a second. Now, when it comes to calculating it, an eta squared score, if you're running your data in Jamovi, Jamovi will provide an eta squared score. You do have to tell Jamovi that you would like it to measure effect size. So there's a box we can go over if you need to have effect size for one of your variables. You just check a box, but it is optional. It doesn't automatically give you this, but it's easy. I'd also like you to know how to calculate an eta squared score yourself by using a few numbers from your data source table. So what numbers do you need from a data source table to be able to calculate an eta squared score? Pretty easy. Eta squared score is really a sum of squared between versus total sum of squares score. We've talked through how to get these numbers when we did our one-way ANOVA, like a really simple ANOVA. You can get these out of your source table pretty easily. So you just have a couple of numbers to add up and then do a division going on here. You can calculate, again, an effect size for each possible main effect you have. You also can calculate an effect size for an interaction. Again, you would only ever calculate it and report it if you had a statistically significant main effect or if you had a statistically significant interaction. So let's do a little practice of that just so you know where these numbers are coming from. Let's say we did a study looking at the effects of the sex of a teacher, being either male or female, and the effect of encouragement, meaning either the teacher provided encouragement to students or just didn't say anything encouraging, and to see how these two things could have an effect on test score. Let's say we found a statistically significant main effect of sex of teacher and a significant main effect of encouragement of teacher and a significant interaction between the two. If we did, we would report 3 separate eta squared scores, one for each of those significant effects, right? So how do we get that? Well, remember, if we go back one, eta squared is simply sum of squares between divided by sum of squares total. So here we have a sum of squared score for, let's do the first one, right? What would be the eta squared score for sex of teacher? We would take the sum of squared score for sex of teacher divided by sum of squares total. How do you get the total? You just add them up. 10 plus 7 plus 3 plus 10, you throw in the error. Remember that sum of squares error is a measure of all the other variability in our data that wasn't specifically tied to one of the things we did as our manipulation. So 10 plus 7 plus 3 plus 10 is just 30. So the eta squared score for sex of teacher is 10 divided by 30, which gives you a score of 0.33. If we already said that there was a significant effect of teacher sex on test score, that tells us that scores for people who took a test with a male teacher were different than scores for people who took the test with a female teacher. How much of a difference is us asking what was the size of that effect? So our eta squared score of 0.33, well, what does that number mean? What does an effect size of 0.33 mean? It means that, again, you take that little number, which is 0.33, multiply it by 100 to put into words. An eta squared score of 0.33 means that 33% of the variation in test scores that we had for our participants could be explained or understood simply by knowing, did that participant have a male teacher or a female teacher? Let me say that again to make sure this is making sense. We are looking for not just a measure of whether there was a difference. We already know there's a statistically significant difference in test scores depending on whether you had a male or female teacher in our participants in the study. We want to know how much of an effect. So we calculate our eta squared score, which is again sum of squares of teacher score divided by total sum of squares, which we just add these 4 up together to get our total. That gives us a sum of squares score of 0.33. We multiply it, 0.33 by 100, and it tells us that 33% of the difference in test score in our group can be explained or understood just by knowing sex of teacher. So if you ask me what score am I going to get on this test, one of my questions would be, well, did you have a male or a female teacher? Because about 1/3 of your score is determined by whether you had a male or a female teacher. That's what this data is telling us, right? If you add all of your possible eta squared scores up here, they would equal 100. Why? Because we are just looking for what are the many things that are influencing test score, and all of them together give you your test score. They give you that information, right? Now, it's important to note that if you have a large enough sample size, you can have a statistically significant effect. So it's a real difference between your research groups, but it could still be a very small effect. This is one of the reasons that we are much more often including information on effect size these days if we're writing up a paper. We don't just want to know that there's a difference between groups. We want that next piece of, yeah, but how much of a difference? How much of an impact did this variable have on whatever we're measuring, right? Should we care about it is really that effect size piece. Not just, is there a difference between my groups, but is it enough of a difference that I should care about it? Let's go over a couple of examples of this so you can see what I'm talking about. First one is from some real research that has to do with birth order and IQ. Now, IQ has been traditionally used as a measure of intelligence. We now have a lot of research to suggest this is a flawed measure of intelligence, but we're going to put that aside for now. We're not evaluating whether IQ is a good measure of intelligence. There's good reasons to think it's not, but we have used it in the past. And there have been lots of different studies on what kinds of things seem to influence IQ scores. And one of the questions that has been asked by researchers is whether birth order is related to IQ, meaning do firstborn kids have higher IQs? Do middle children have higher IQs? Do youngest children in the family have higher IQs, or only children? Is there any higher IQ group from these different kinds of birth order groups, right? Well, this one, we have data from tens of thousands, hundreds of thousands of people. We have a ton of data on people's IQ scores and their birth order. So huge sample. And in looking at that data, we have found one particular pattern. This is a statistically significant pattern, meaning that, that this pattern does not appear to be due to chance alone. There is one group that does appear to have higher IQ scores. Got any guesses as whether it's oldest, middle children, youngest, or only children? Well, I might want to brag here a little bit because it's my group, only children. We have statistically higher IQ scores than all of the other birth orders. Everybody else appears to be about the same. But before I get too, self-important about this, we might want to go to the next step and say, but how big of an effect does birth order seem to have on IQ? How much of an effect are we talking here? The answer is tiny. Statistically, it is 1 IQ point higher on average than any other particular birth order. 1 IQ point is kind of nothing, right? Would you want to use this information to tell your friends who have a child and are thinking about having a second, hang on, don't have any more kids. Stop right there or all of your kids will become dummies? No, that would be terrible, right? If you were hiring someone for a job, would you say, I don't need resumes. Just tell me if you are firstborn or not, because I'm going to give this job to a firstborn person. Everybody else, I won't even consider you. No, of course not. 1 IQ point is nothing. This is a real effect, but its effect size is so small that we shouldn't use that information to do anything in our lives, really. Another example that's kind of recent, actually, that's come out is the relationship between bacon and cancer. This is a really good real-life example of looking at p-values and effect size, I think. Pretty recently, a couple years ago, we had some research that came out that made all local newspapers, national newspapers, right? Big bold letters, bacon and other cured meats cause cancer. This is coming from research. First question to ask is there a real relationship between eating cured or red meats? Cured meats are things like salami, hot dogs, bacon. They're all cured meats. Red meat, is beef, right? Any relationship between eating those and developing cancer? And the answer is yes. There is a statistically significant link. Meat and cancer, how strong is the evidence that there's a relationship between eating, especially these cured meats, and cancer? Really good evidence, right? This is called group 1 carcinogen, meaning these are the things that we feel most comfortable in saying, yes, they can cause cancer. Slightly less sure is called group 2A classification. Group 2A means we're going to say as scientists, this probably causes cancer. And scientists are cautious. So probably means, yeah, there's a really good chance. Eating pork, beef, and lamb go into that 2A category. By the way, group 1 category, what else is in there? Smoking. So we are as sure that eating cured meats causes cancer as we are sure that smoking causes cancer. So, first part, is there a real link? Yep. Very comfortable saying there's a real link. But you know what? There's a lot of people who really enjoy eating a hot dog sometimes, eating some bacon, eating a little bit of salami on a charcuterie board. And they're like, but okay, I mean, I guess, but I really want to have an excuse to keep eating bacon sometimes. So they ask the second question, which is a good question to ask, which is, what is the effect size of eating cured meat? Okay, so eating cured meat can cause cancer, but how much of an effect does eating cured meat have in terms of your cancer risk, right? Is it really as dangerous as smoking? Okay, we're just as sure that cat on the left smoking a cigarette, that cigarette smoking causes cancer. We're as sure as cat on the right eating some bacon. But does that mean that eating cured meat is as likely to cause cancer as smoking is? Is it as dangerous as smoking? No, not necessarily, and this is where effect size comes in. Basically, this research says that the link between red meat and cancer, or really the link between cured meat, like bacon, and cancer, is as certain as the link between smoking and cancer, right? This is like saying that it has a 0.01 p-value. So we're pretty darn sure, yes. But it says nothing about effect size yet. Both could be true relationships in the world, but one could be a much stronger relationship than the other. And in fact, that's exactly what it looks like when it comes to smoking versus eating cured meats and cancer. So, as a follow-up to ask what's the effect size of eating cured meats and getting cancer, the results showed that those who ate the most processed meat had around a 17% higher chance of developing bowel cancer in particular, compared to the group that they studied that ate the least cured meat. And by the way, eat the least cured meat are probably going to be vegans who eat zero cured meat. Now, they have a 17% higher risk of bowel cancer if you eat a lot of cured meat versus you eat none. Seems like a big number, but it's a relative risk. So let's put it into perspective and convert it into absolute numbers. We know, and by the way, this study was done in the UK. So we look at data from the UK. Right? Let's look at what's the risk. Actually, before we go to our little graphic, we know that out of every 1,000 people in the UK, about 61 will develop bowel cancer at some point in their lives. Bowel cancer is honestly not the most common cancer, but it's the only one that does seem to be influenced by whether or not you eat cured meat. Okay, so out of every 1,000 people, 61 will develop bowel cancer. Those who ate the lowest amount of processed meat are likely to have a lower lifetime risk of bowel cancer, only 56 cases in 1,000 instead of 61. For those who ate the most amount of processed meat, their chances were 66 out of 1,000 instead of the average of 61. So a little higher than average. If you never ate cured meat, a little lower than average. Notice it's bigger, but it's still not very likely that you would get bowel cancer. And it's not a huge difference between eating the most possible cured meat and eating no. And by the way, the group that eats the lowest cured meat is 0. The ones who eat the highest cured meat are eating, I think it was 3 or 4 servings of cured meat on average a day. Do you eat 3 or 4 servings of cured meat a day? Are you eating some kind of sausage or bacon or salami 3 or 4 servings every day? I don't think many of us, even those of us who might like bacon and hot dogs, I think most of us don't eat that much a day. Most of us are in an in-between category, which there was no meaningful difference between us and never eating it at all. So maybe don't eat it 3 or 4 times a day to decrease your chances of cancer, I guess. But you're not putting yourself at the same kind of risk as smokers. Here's another graphic of an analysis that came out of this, comparing tobacco versus meat. Some things to notice: cancer is caused by tobacco, 86 of all lung cancers, and 19% of all total cancer appears to be caused by tobacco use. On the other hand, cancers caused by processed meat, 21% of bowel cancers, or 3% of all total cancers. So meat is not related to causing nearly as many kinds of cancer and nearly the common kinds of cancer as lung cancer is. So if we look at it another way, research suggests that if no one smoked, there would be 64,500 fewer cases of cancer per year in the UK. But if instead no one ate processed red meat, or processed meat or red meat, it would cut down on 8,800 cases of cancer. Also, I don't know if it's worth mentioning, bowel cancer is a lot easier to treat than lung cancer. Not that you really want any kind of cancer, right? All this boils down to effect size. Absolutely, eating cured and red meats, well, at least eating cured meats, we are as certain that those can cause cancer as we are smoking. But do they have as much of an effect? No, definitely not. And I kind of liked this little tweet that came out after all of this discussion of the research. Stubborn love of bacon just taught more Americans the difference between p-values and effect size than 100 stats courses could. That is probably true. People were really desperate to find a way to justify continuing to eat bacon when all of these bacon cancer headlines came out. But it's not that they're wrong, right? It's definitely worth going beyond just saying, is there a significant effect? Is there a significant difference between my groups? Good to go the one step further and say, but how much of an effect is there? When we go through your analyses for experimental, and also when you go through your analysis for senior thesis, you should certainly talk to your instructor. You will definitely be talking to me for experimental to just kind of figure out, do I have to do a measure of effect size for whatever my stat is that I'm running? What would the most appropriate measure of effect size be? Run that, and then make sure you understand, do I need to report an effect size or no? The answer is always, if you found a significant effect, you report effect size. And then finally, what does this number mean, right? This calculation. I will happily walk through it with you to understand what exactly does this number mean in, regular English words. And we'll put those in our paper as well. Thank you for your feedback, Fennel.